Before we get started, I'll show you what all we've got set up here. You're looking at the HHO tank right here. I've got a number of stainless steel plates which are connected via some stainless steel rods, but they're non-contacting and they're connected in parallel. So one plate will be positive, the next one will be negative, the next one positive, so on and so forth. As I pan around here, you see the back of the tank where I'm coming in. One lead of the tank is going directly into the negative side of the power supply. The other lead is going into the source of a transistor, and then the positive side is going into the drain of the transistor, which is here on the center. I've got a signal generator hooked up to the source in the gate, which is going to be switching the transistor at a specific frequency. And if you can see down here, I've got the transistor just in a vise, which is my makeshift heat sink. Pan over here, you can see the digital power supply set up. Voltage reading is on the right, amperage on the left. Over here I have an Agilent 3322A signal generator. This generator will go from 0 to 20 megahertz with a resolution down to 1 microhertz. So we can go 6 decimal places in resolution in fractional hertz, which is going to be very important because the way that this resonant frequency sets up, it's sensitive down to about a 10,000th of a hertz. So that's what our setup is there. So we're going to come over here and I'm going to mount this thing on the tripod and get ready to run the demo for you. This is a fairly unique situation in that we can take the frequency which we're switching the transistor at and actually reflect the energy coming all the way back to the source. And I'll show you how we're actually able to zero out the amperage coming from the power supply. I'm going to turn on a light here so that you can see the tank whenever it starts boiling and making hydrogen, and at the same time you can see the amp meter off in the distance of the power supply. First quick experiment I'll show you. We'll just disconnect the power supply to the transistor and we'll run the power from the power supply directly to the tank itself without switching anything. So I'm going to come over here. I'm going to disconnect this here. I'm going to connect this here. I'm going to turn the power supply up to about 7 volts, which will be the reading on the right hand side of the power supply, and you can see what kind of current going directly into the tank at 7 volts this thing produces. So we'll crank it up. And oh, I forgot. Just a minute. I gotta come over here. I gotta connect this. I didn't have this even connected in, so let me connect this as well. Alright, here we go again, going up to 7 volts. Okay, coming off the power supply at 7 volts, we're pulling about 12.5 amps. Let me give a little bit of a zoom here. There. So now you can see, and obviously you can see that the tank is just pouring hydrogen off of the plates. Okay. Let me pan a little bit more. So we're looking at right at 7 volts, 11.9 amps. Okay. Now we're going to disconnect right here. Oops, wrong way. Alright. So we'll turn this off. I'll let the bubbles settle in the tank. Now the next thing we're going to do, I'm going to come over here. I'm going to connect the transistor to the tank. I'm going to come over here and connect the power supply to the drain of the transistor. And what we're going to do to start with is we're going to essentially, I'm going to bring the signal generator pretty close, try to get fairly close to where I know the frequency range is here. And I'm going to engage the signal generator and turn it on. And then we're going to go back and we're going to start cranking the power up again. So I'm going to run it at 7 volts, which is where it was before when it peaked out at about 12 amps. And what you're going to see to begin with here is you're going to see the amperage rise and fall when we start cranking this thing up. And let's see here. Okay. Interestingly enough, sometimes I get lucky and hit it right on the frequency when I tune it in. So now you can see 7.1 volts. You can see the tank. Now you're starting to see it trigger up. Okay. So essentially you're watching the amperage rise. Now what I'm going to do, I'm going to keep an eye on that, and I'm going to switch the signal generator. And when I do, I'm going to play around with the frequency a little bit to come in to try to tune this thing. Right now it's peaking out, which means okay, now it's dropping back down. And it takes a minute to lock this thing in. It'll go up and down, up and down, up and down. You're seeing 7 volts on that side. Okay, it's starting to rise again. Once I get close to the frequency that it needs to be at, I can kind of lock it in to where it won't rise and fall. Now I'm peaking it out at 9.5, and actually, let's see if I can drop it down. There we go. Now it's dropping back down. What I want it to do is just drop slowly. Okay. I'm tuning it over here with my signal generator, and I'm literally adjusting the frequency at 1,000th of a hertz. All the while we're generating gas. Now we're locking in the power supply current, and as best as what I can tell, we're matching the frequency of the pulse so that whenever the plates discharge through the water, we're getting the reflective energy back and it's meeting the positive energy going forward. Now once I get this thing really tuned, that thing will stay locked on 0 amps indefinitely. And it's like matching the output pulse. Now it's starting to climb again. So what I'll do is I'll go over here and I'll start finding where my frequency needs to be. And if I get real close, see, I can stop it. Let's see if we can tune it. Now it's not rising. Now we're going to drop it back down. It's like tuning a radio. And the more I work with it, the further I go. Right now I'm adjusting the frequency at 1/1000th of a hertz. Here it comes dropping on down. 3.2, 0.1, 0. You can see at the bottom of the video the tank, it's just pouring off the hydrogen from the plates. And look at the power supply, and we're keeping it steady so that the reflective energy is equal to the outgoing energy going into the system. And the power supply is being zeroed out to where there's no current that's being able to be measured into the circuit. There is electrical current going out, but it's being matched with reflective energy going back so that the power supply amp meter zeroes out. We will shoot another video with a battery and a Hall sensor to verify that the same thing is going on, that the Hall sensor does not sense any magnetic field in the circuit, and so somehow we're able to reflect the energy back to the system. The problem we have up to this point is that the experimentation that I've done in running batteries off of it. Here we go, just a minute, let me retune this thing. As it climbs, I've got to tick it up so that, alright, let me bring it on up a little bit more. Now I'm going to start bringing it down. This is highly sensitive too. Right now I'm tuning at 1/1000th of a hertz. You know you're close whenever it drops down very slowly. If it rises and falls too quickly, you're not close to the matching frequency of the output and reflective energy going back. We're maintaining it at 7.1 volts, which means that if we were directly connected the power supply to the tank, it'd be pulling about 12 amps off of the power supply. You'll also notice that that orange crud that you see at the top of the water is actually the minerals of the water. As it's breaking down the water, the minerals are being released. It's not iron. Those are non-magnetic stainless steel plates, and they do not rust. Now, this is just city water that's being poured into the tank, and it's cruddy as all get out. We're still maintaining 0 amps on the measurement from the power supply. And we've got some fairly vigorous bubbling action going on. My experience has been the first couple of minutes it takes to lock in the signal, and once you get locked in, it'll stay locked in almost indefinitely. I get it to the point to where I'll start trimming it. You notice that it's ticked up to 1/10 of an amp. I'll come over here, there's 2. Now I'll trim the signal generator. 3, 4, let me trim the signal generator. Alright, back down it goes. I'll pull this up so that the next time that the power goes up, that little knob that's in the upper left hand corner of the video, you'll see how I'll take it with my thumb and turn it, and what it does is it literally trims it at whatever setting I've got the signal generator on, which right now I've got it set up so that we can trim it at 1/1000th of a hertz. I can toggle it over any direction, and we can trim it at 1/10 of a hertz or a 10,000th of a hertz. Nice little signal generator, a lot of versatility. Get a better view of the bubbles coming off the top of the tank. That's the reason why I have the light shining on it. problem I get is once I get into developing this and working with it for 5 or 10 minutes, pretty soon I hardly ever have to trim it at all. So hopefully in a minute it'll start moving a little bit out of resonance, and you'll be able to watch how I can spin the thumb wheel on the signal generator and bring it back in. We're developing some nice bubbles. Here we go. Okay, keep an eye on the magic thumb wheel. As I rotate this knob, I'm going to bring the frequency, and there it goes, back down. I'm still only tuning it at 1,000th of a hertz. In a minute, as I get the signal even more locked in, I'll switch over and I'll start tuning it at a 10,000th of a hertz. Once we perfectly match it, I can leave it alone and the thing will run for hours, and the amp meter will essentially show no amperage. These water tanks behave like a large capacitor, because essentially that's what they are, and the water is the dielectric. And obviously all capacitors have a resonant frequency, and so do these tanks. Here we go. 0.2, okay, turn the thumb wheel. That adjustment took it down to 1,000ths of a hertz. Now I'm going to switch over. I'm going to be at 1/10,000th of a hertz now whenever I start adjusting my rotation. We're getting pretty fine resolution here. Also, I'll turn up the voltage on this side, which actually would theoretically pull the current up. Let's take it up to about 7.6, 7.7 volts. Interestingly enough, you notice the current doesn't even change, even though we're pushing more power into it. We're pretty close on the mark. Here we go. Let's change it up. Because I'm rotating at a 10,000th of a hertz, I have to do more spins on my thumb wheel to trim it. Now it's going to drop very slow because the frequencies are getting more finely tuned. The Stan Meyer material claimed that he was breaking down water by resonant frequencies and he was using very little current. This is not the same thing. There is current going into the system. Somehow we're able to take the current and match the reflective energy coming back when we're switching the transistor on and off. our key is going to be to take this reflective energy and return it to the system, such as a battery or an ultracapacitor, whatever we want to use as our initial power source to break down the water. It's a very interesting phenomenon, and it takes place in an extremely narrow frequency range. It's a frequency range that is between a single hertz, where it's always above 1 hertz level, and as far as down to single digits, and down to and beneath the other. Now you'll notice we're pushing at 7.6 volts, and the amp meter on the power supply is at 0. Now I'm going to go over here. This is pretty much demonstrated that we can tune it pretty accurately. I'm going to turn off the power supply for just a second. Notice we're at 7.7 to 7.8 volts and it's showing 0 amps. So we'll turn this off. I'm going to turn off my signal generator. Now what I'm going to do is I'm going to directly, I'll connect this one over here because it will pull a lot more current, so I need a bigger wire. I'm going to directly come in here. Now we're going to go back up to 7.7 volts, which is where we finished off before, and we'll see how much current. 7.7 volts is about 15 amps, almost 16. We're getting more hydrogen at that level simply because we're not running a duty cycle. It's constantly flowing instead of pulsing. However, we could raise the voltage significantly with the pulsing effect and essentially get the same amount of gas, but we'd have to run it at a higher voltage level. So what we can show here is that 7.7 volts directly into the tank, it pulls over 15, almost 16 amps, and through trimming this with a transistor and setting the perfect resonant frequency, we can zero out the amperage at the same voltage. So now our mission is to take this reflective energy and return it back to the system, and that's going to be where the trick lies. That'll conclude our demonstration for now. Talk to you later, Jeff. Bye.